Okay, so let me welcome you on yet another seminar of the Code Research Group. Our today's speaker is Adam Kabela, currently uh, at the University of West Bohemia, and previously, and the work probably was done when he was a postdoc in Berlin. So Adam, please.
Okay. Thanks for the opportunity. I'd like to talk about permutations and their densities and density maximizers for a little bit. This is not what I usually do. I usually do graph coloring, but with Dan and John and Daryl, we did this little project on layered permutations. So this is it for today. For starters, I should recall the concepts used throughout the talk. Here is how you think of permutation density. So think of the permutation written here, the permutation 2, 4, 1, 5, 3, and think of substrings of length 3, right? Now there's 10 different ways how to choose a substring of length 3. Yet only one of those ways is the pattern 3, 1, 2. So we say that the density of the permutation 3, 1, 2 in the permutation 2, 4, 1, 5, 3 is 1 over 10. Right? So, this is permutation density. And so the second concept used is the notion of layered permutations. Have a look at the picture. So this is a particular example of a layered permutation. Consists of 3 layers. The length of the first layer is 13, the length of the second layer is 1, the length of the third layer is 2. So in particular, this is permutation of total length 16. It goes as written up here. It has 3 layers. So this is an example of layered permutation. Now there's 2 equivalent ways how to define layered permutations. So one would be describe structure. That is there are these layers, and within each layer the permutation is decreasing, and layer-wise, I mean, the consecutive layers are increasing. The values through the layers concept. Thinking of layers consecutively, their values are increasing. That's one way. Another way would be another equivalent function would be via forbidding patterns, right? So you can say that the permutation is layered if it avoids the patterns 3, 1, 2 and 2, 3, 1. Right. So this is layered permutations. One last thing. The permutation in the figure has 3 layers. First of length 13, second of length 1, third of length 2. Now, I would call the layers of length 1 singleton layers, or simply singletons throughout. these are the concepts. Now, what's it about? It's about maximizing density of a layered pattern. Right? So we have a layered permutation. We think of it as a pattern, and we'd like to find larger permutations, maximizing the density of the pattern. Now, the good thing is, shown by this group of authors, the good thing is that for every layered permutation, there always is a maximizer which is also layered. And that's for every length of the maximizer. And also note that the singleton layers two on the top would play a fundamental role in the structure. So the singleton layers in the pattern play a fundamental role for the structure of the maximizers. So here is a first instance of this phenomenon, namely that if there is no singleton layer in the pattern, then all the maximizers are layered. Right? So with this theorem on hand, we know that for every layered pattern there's a layered maximizer. So now we can think about how many layers are there in the maximizer. And this is what the talk will be about. And we'd like to think of longer and longer maximizers. So we'd like to think of a sequence of permutations maximizing the density of the pattern, where the length of the permutations in the sequence goes to infinity. So as the length of the permutations goes to infinity, well, the density goes to some constant, and this constant would be called packing density of the pattern. Now here's the first result on that regard. So think of the permutations 1, 3, 2. So it's a layered permutation. It has two layers. First layer is a singleton. Second layer is of size 2. It's known, and it's been shown by different authors independently. It's known that the maximizers, the number of layers of the maximizers of this pattern goes to infinity as the length of the maximizer grows. And the figure shows the structure of long maximizers. So simply spoken, if you want to maximize density of permutations permutation 1, 3, 2, you can use a long permutation of roughly this structure, as shown in the figure. Now, when you think about it, intuitively makes some sense. So think of the permutation 1, 3, 2, and think of the maximizer. Namely, think of the first layer of the maximizer. Now, if the first layer was reasonably long, you can always split the first layer into 2 and improve the density, right? So by splitting the first layer into two, you can always sample the singleton of the pattern even as the layer gets split. Yet, you improved a little bit because now that the first layer is split into two, you can there's a tiny chance you sample the whole pattern from the newly established first two layers, right? So this should be the intuition for the fact that in the structure the first layer is real tiny. In fact, the number of layers goes to infinity. The layers getting tinier and tinier as you get closer and closer to the start of the and people did the calculations, and we know the optimal density of the permutation. So this is a particular example of a pattern for which in the layer maximizers the number of their layers goes to infinity. So here's another example. Again, it shows significance of the singleton layers in the pattern. Namely, if there's no singleton layer in the pattern, we can bound a number of layers in the maximum. That's what this proposition says. And there's more results of this flavor. There's more, for instance, in the paper of Albert et al., in the paper of this group of authors, there's elsewhere, there's more results of this flavor. There's results showing that somehow the singleton layers in the pattern play a role regarding the number of layers in the So this is a little bit of the background. Now, there's a conjecture. So a natural question in this context, a natural question would be, well, what are the sufficient conditions for the pattern in order to be able to bound the number of layers in its maximizers? And here's a suggestion, and it's a reasonable suggestion. It suggests that the first layer should not be in the pattern. The first layer should not be a singleton, because we saw an example of a pattern for which the number of layers in the maximizers cannot be bound. Similarly, the last layer should not be a singleton. You can just think of the example reversed. And furthermore, there's no two singleton layers in the pattern should be consecutive. I guess it should be relatively easy to think of a pattern having two consecutive singleton layers and showing that indeed number of layers in its maximizers goes. So this is a guess for sufficient condition to be able to bound the number of layers in the maximum. Unfortunately, turns out not to be true, and first thing I'd like to talk about in a little bit more detail is a counterexample. So in order to disprove the conjecture, we'd like to think in the limit, in the limit version of that story. So instead of talking permutations, we talk permutons, which is a limit object for a sequence of permutations. Similarly, as in for a sequence of graphs, we have graph forms. Similarly, for a sequence of permutations, we have permutons, right? So we talk permutons, and we can define layered permutons similarly as we define layered permutations. So here's what we show. We show that for a pattern whose first layer is very long and second layer is singleton. For such pattern, the number of layers in the maximizers goes to infinity. Here's how we prove that. For the sake of a contradiction, we suppose there's a layered permuton maximizing the density of the pattern and having only finitely many layers. In addition, we assume that all of those layers are of non-zero measure. So this permuton maximizes the density of the pattern, and here's the first step of the proof. So it gets a little technical, but the proof is relatively short, and I hope to be able to walk you through the entire proof, show a pretty detailed overview of how it's done. So here's the first step. So it's just a funny way of writing packing density of the pattern. So we have a layered permuton with finitely many layers. We suppose that it has the desired density, and this is just a funny way of expressing this density. So the x subscript 1 is the length of the first layer of the maximizer. So the x subscript 1 power to n means we think of sampling endpoints from the first layer of the maximizer. Right? So this part concerns a scenario in which the first layer of the pattern is sampled from the first layer of the maximizer, and the second layer of the pattern is sampled from the second layer of the maximizer, and the rest is sampled. The sampling of the rest is encaptured by this sample. Right? So the second term concerns the scenario in which first layer is sampled from the first layer of the maximizer. Second layer is not, the second layer of the maximizer is not used this time, and the rest is sampled according to this. Similarly, third term concerns the scenario where when the first layer of the maximizer is not used, the first layer of the pattern is sampled from the second layer of the maximizer, etc. Indeed, this is just a funny technical way of expressing density. The second step would be to think of these capital sigmas, of these auxiliary sums. We note that all the sums are positive, all the sums are at most one, and there's a chain of inequalities. Third step would be to think of this A, of this auxiliary coefficient of distributing over the layers throughout sampling. So recall the definition of the A, and for the sake of simplicity, in proving this theorem, we would not give an explicit threshold on n. We would only show that such n exists, right? We would only show that this works for sufficiently large n. Now, in order to do that, we think of A as a function of n, and we think what happens as n goes to infinity. And we recall the definition of A, and we note that as n goes to infinity, A is roughly of this size. Similarly, we view the packing density of the pattern as a function of n, and we think what happens as n goes to infinity. We'd like to show that as n goes to infinity, packing density does not go to 0. It goes to some constant, perhaps. Here's how we did that. So we did that simply by exhibiting construction. So we think of permutation pi prime, which is simply the permutation obtained from the pattern considered by removing its first layer. So pi prime, in other words, pi prime is a layered permutation having k plus 1 layers of sizes 1, L subscript 1, L subscript 2, etc., L subscript k, respectively. Right? So it has k plus 1 layers, and then their sizes are 1, L subscript 1, and so on. So that's what pi prime is. Now, the construction goes as follows. We think of a permuton, of a layered permuton, maximizing the density of pi prime, and we extend this permuton by adding a long layer at the very start and rescaling. So the resulting permuton looks as follows. Its first layer is really long, and the rest is just a rescaled layered maximizer of pi prime. Now think of the resulting permuton and think of sampling pattern pi from that permuton. So in particular, if we sample n points from the first long layer and the remaining points from the remainder, so that the remaining points give a copy of pi prime, then we're happy because we just sampled the pattern pi. So this is what this term is about. So this is probability of sampling n points from the long first layer. This is the probability of sampling L points from the remainder times the probability that this remainder gives permutation pi prime. And this is just a factor on how this could be sampled. So this whole thing gives a lower bound on the density of pi in the auxiliary permutation. And because the permutation we originally considered is optimal, it's maximizing the density of pi. So this lower bound also works for the permutation we consider for the maximizer. Right, so we get this inequality. Recall that we'd like to show that packing density of pi does not go to 0. So to do that, we simply consider the right-hand side of the inequality and see what happens as n goes to infinity. And and we know that as n goes to infinity, this goes to final constant like that. So all in all, we can lower bound the packing density of pi by something which is positive. That means that the packing density of pi does not go to 0 and means that it's roughly of this magnitude. Basically, what we are trying to do through our proof is to think of claim 1 and try to find upper bounds or lower bounds for everything that you can see in claim 1. Now, once we do that, once we bound everything, hopefully we get a contradiction. We continue in this session. So we've already bounded A and the packing density and the auxiliary sigmas. Now we'd like to bound X2. And so we show this inequality. We do it in 2 steps. First, we show that X1 cannot be smaller than X2. And in order to do that, we think of the permutation considered, that is the permutation maximizing the density of phi. We think of the first 2 layers of the maximizer, and we think what happens if we just swap the first 2 layers. Now, before swapping, it was a maximizer, right? So when we swap, the density should not increase. meaning that this quantity should not be positive. So again, what this inequality says are the first part of the left-hand side. Okay, let me put it like this. When we swap the first layers, perhaps most of the sampling remain the same. The only sampling that are different are those using both of those layers, right? If we didn't use both of the first two layers in the sampling, well, nothing changes when the first two layers are swapped. So the only difference is when both of them are used. And this is written formally at the left-hand side of the input. This is the difference in the densities. First term is after swapping, second is before swapping. And by the optimality of the permutation considered, this difference should not be positive. And we get that x1 is greater equal x2. Next, we use this show that in fact it is much larger. In order to do that, once again, we think of the permutation considered, that is the permutation maximizing density of pi. We think of the first two layers of the permutation, and we think maybe we can take the first layer, cut just a tiny bit of it, just an epsilon bit of it, and add it to the second layer. Formally, what we do is that the thing that we cut from the first layer and add to the second layer, this size is denoted by y. This size is denoted by y. And we think of the density in the resulting permutation as a function of y. So again, this is just a funny way how to write the density in the tweaked permutation as a function of y. And once again, by the optimality, by the maximality. So when we do this tweak, the density should not increase, right? So in particular, the partial derivative of f evaluated at 0 should not be positive. Because if it was, we could just do a small tiny change, cut a tiny bit from the first layer, add it to the second layer, so the density would increase, and this would contradict the assumption that our permutation is not. Right? So the partial derivative evaluated at 0 should not be positive. And so we take this function, we derive, we employ this idea, and we get roughly this. Right. Now, using that x1 is greater or equal x2, we note that the second term is non-negative. Right? Thus, the first term cannot be positive, cause the inequality. Because the first term cannot be positive, we get the desired inequality. That is, x1 is actually much larger than x2. Right? So we are almost there. Next thing, B bound is x1. Now, the idea here is to, once again, think of the maximizer, and now replace second layer of the maximizer with a scaled copy of the maximizer of pi prime. Everything remains the same, except the second layer is replaced by many layers which resemble the maximizer of pi prime, except they're scaled to the size of the layer replaced. So here the calculations got a little bit more technical, but we got the following found on x1. Last step, once again, we think of the considered maximizer and we tweak it a little bit. The last tweak would be that we merge the first and second layer of the maximizer. Again, we do this idea, all right, so by tweaking the permutation, the density should not increase. Here the tweak is merging the first and second layer. The density should not increase, and we obtain an inequality like this. And basically that's that. So with claims 2, 3, 4, 5, 6, 7, we did bound everything that appears in claim 1. So now we use that all and we get back to claim 1 and note that the left-hand side of claim 1 is some constant, whereas the right-hand side goes to 0 relatively quickly. And that's the desired contradiction, right? So for starters, we suppose that there is a layered permutation maximizing the density having finitely many layers. And now we get the contradiction. Which one? So that's that. So for the sake of simplicity, we only argued that there exists sufficiently large n. Now, going a bit more in detail, inspecting the proof in a little bit more detail, it actually gives a particular, relatively small particular example of a layer permutation for which the maximizers, the number of layers of its maximizers goes to infinity. So a particular small counterexample would be a layer permutation having 3 layers of sizes 13, 1, and 2. So that's the first thing I wanted to talk about. So, second thing, is there a way to fix that conjecture? Right? As stated, unfortunately, it doesn't work. So, is there additional assumptions so that the new conjecture will work? So here we are not quite sure what the assumptions should be. So here is what we can prove for now. We can prove that for a length permutation such that no 2 singleton layers are consecutive and the first and last layer are non-singleton. So these are the original assumption of the original conjecture. The additional assumption being that the first and last layer are of the same length and no non-singleton layer is shorter. So with these additional assumptions, we can show that the conjecture is true in the limit version. So this is a little improvised. You're not quite sure what the natural additional assumption should be. Right. That's all I wanted to say today. Thanks for listening.
Okay. So, many thanks. So, are there any questions for Andre? You always have some questions.
I could only have one stupid question. I mean, you're writing there 2022 plus, so you're sure that you will not publish it this year?
No, it's not that. Sorry, it's my bad. So when preparing the beamer, used replace. So that there's this only feature in the beamer, right? So we want something to be only displayed on click 21, right?
Okay.
So I used that. I wanted this inequality only to be displayed on click 21 on this slide. Then I realized, oh damn, I want it to be displayed on click 22. So I replaced 21 with 22 throughout the whole source, and I didn't realize that my bad. I hope, to answer your question, I hope that the manuscript should appear soon on archive. Yeah.
Okay, that was nice. Are there any other questions for Adam?
Okay, so you have this theorem there. Do you have your own conjecture on what's the right characterization?
Yeah, we don't. Unfortunately, we don't. So the results known. So there's a pretty decent number of known results for patterns of particular restricted type. We know what their maximisers are, right? Problem is, even though there's a number of results, most of them concern only patterns of a very simple structure, very restricted patterns, right? So what seems to be clear is that it's the singleton layers playing the key role. what seems not to be clear, at least not to me, what the role is exactly. Yeah, we don't have a new conjecture. We can only show that with these quite strong additional assumptions, the conjecture works.
Maybe one more question. So, are there known permutations for which have both finite and infinite maximizers, like with finite and infinite many layers?
Yeah, I didn't find any. Don't know if there are, but in the paper of Albert et al., they introduce this conjecture saying that there's an interesting dichotomy, and they give examples of permutations for which the number of layers of their maximizers is always bounded, and they give examples of permutations for which the number of layers in their maximizers is always unbounded, and they call this an interesting dichotomy. So I don't know, maybe they think that,
I was just wondering, I mean, like showing that every maximizer is infinite is something different than showing that there is a maximizer that is infinite or something. So maybe like characterizing those that have some maximizer that is infinite might be easier than or so.
Yeah. As I said, I'm not usually a permutation researcher, but so I'm not an expert here. But for me at least, this seems like a very interesting question. Is there a pattern for which both can happen? I don't think it's common.
Okay, thanks.
Okay, many thanks. Any other questions? No. So let us thank the speaker yet again. And that's it for the seminar for today.